Hey, in this video, I'll give a deep introduction into the complex numbers and try to give a different insight into what is a complex number. Now it all starts with the definition of I. I is defined to be the square root of -1. Yes, we are taught in school that we don't take square root of negative numbers, but taking a step forward, we define the square root of the negative number -1 to be the number I. With the definition of I, now we can go ahead and define the complex number. So let's define the complex number z. This number is going to be x plus iy. That is for the time being. Later we'll see a different version of the complex numbers. For now, z being x plus yi means that x is the real part of the number, while iy is the imaginary part of the complex number. Later, we will see the polar presentation of the complex number, r times e to the I theta. But for now, we're going to focus on the algebraic presentation, x plus iy. In order to understand the numbers a little bit better, let's add another complex number, w. W is going to be a plus ib. Again, a would be the real part of w, while ib is the imaginary part. Now, having two complex numbers, we can define the sum of z and w. For now, and soon we'll understand why, we're going to define that z plus w is x plus a, the two real parts of each number, plus I times y plus b, the imaginary counterparts of those numbers. Now this number that we have is a complex number on its own. Soon we'll see and understand exactly what it means. Before we move on, I want to focus on two more important numbers. The first one is the conjugate complex number of z, usually marked by z bar, and it is the number x minus iy. All we did was transform in the plus before the iy into a minus. And the second number is the absolute value of z, which is the square root of x squared plus y squared. Now, for those of you who see Pythagoras' theorem here in absolute z, you're right. Soon we'll understand exactly why it's there. Now we're ready to dive deeper and really understand the complex numbers. So let's take z equals x plus iy and w equals a plus ib and take a real good look at them. Now, in order to look at them and really see them, we need to add the complex plane, Gauss plane, the plane where we use the same x and y axes, only this time the x-axis represents the real numbers, whereas the y-axis represents the imaginary numbers. Just like we can see. Now let's look at the complex number z. Its real value is x. We're going to place x on the real number axis, and we're going to represent it by an arrow that represents its size. On the other hand, the imaginary part should be placed on the imaginary axis. Now we use arrows to describe the real part and the imaginary part of a complex number, very much like with vectors. There's a lot of similarity between complex numbers and vectors. They behave in a lot of ways very similar. In this case, z can be represented by an arrow just like a vector. It is a combination of the two arrows that are on the x and the y axis. And now we have a new arrow. Now that we see the number and it is in front of us, we can understand it a little bit better. The first thing we should notice is the length or the size of the number. This is represented by the length of the arrow. Just like we said, the absolute value of z, which is the size of this number, is the square root of x squared plus y squared. And now we can understand why. Looking at the right angle that is created by both x and y, we realize that using Pythagorean, we have the length of z within this triangle. Later, we'll expand even more about the length of z. And what about the conjugate of the number? Well, we said before, it's x minus iy. If we compare it to the original number, to z, that is equal x plus iy, we notice that both of them have the same real part, x. The difference now is that the conjugate, its imaginary part, is minus yi, which means the imaginary part is y units only directed downwards. And this is a reflection of z in respect to the real number axis. Now let's add w to the equation, or more precisely, to the complex plane. Just like before, w also has a real part, which is a, and its imaginary part, which is b. And now we can see w as well as an arrow. Before, I stated that z plus w is going to be the summation of x and a plus I times y plus b. Now let's understand it a little bit better. Just like vectors, when you sum up vectors, you can imagine it as if you put the tip of the second vector on the head of the first vector. Here we're going to do the same. The tip of w can be placed on the head of the arrow that represents the complex number z. That is, when we sum up z and w, it's just like putting the arrows on top of each other. And now we have a new arrow that represents the sum of the two complex numbers. Now let's break it apart into its elements. We see that on the real part, we have x plus a, whereas on the imaginary axis, we receive y plus b. So visualizing it now makes a lot of sense why summing up complex numbers is done the way that it does. Now, the algebraic presentation of a complex number, x plus ib, has a lot of advantages. It's really easy to sum up numbers or subtract numbers, but it also has disadvantages. Multiplying complex numbers or finding a certain power of a complex number can be quite difficult with algebraic presentation. So let us now understand another presentation of a complex number, the polar presentation, r times e to the I theta. Now this presentation has a lot of advantages as well as disadvantages, just like the other presentation. In order to understand it, first we need to remember Euler's identity, which states that e to the I theta is cosine theta plus I sine theta. It is basically the same thing. Now that we know that, r to the ei theta can be represented as r times cosine theta plus I sine theta. If we open parentheses, we get r cosine theta plus I r sine theta. What I would like to clarify now is that the algebraic and polar presentations are the same. Well, they're very much different, but they represent the same number. Let's use some trigonometry in order to explain it. So first, under polar presentation, we need to understand what r and theta represent. So r represents the length of that arrow. We already discussed it. And that r is the square root of x squared plus y squared. It's that distance. While theta is the angle from the real axis, the real number axis, to the arrow of the complex number. If we do that, now in the right triangle that we have, sine theta is y over r, which means that r times sine theta is y, while cosine theta is x over r, which means that r cosine theta is x. So let's review what we have. X basically coincides with r cosine theta, while y coincides with r sine theta, which means that x plus iy is cosine theta plus ir sine theta, which means x plus iy is r times e to the I theta. In the next lesson, we'll understand exactly what are the advantages of the polar presentation of a complex number and also what are the disadvantages. So, see you then.